This is a gate problem that came in the EC paper for 2023 and it is on diodes. But these sort of questions can also appear in the instrumentation engineering paper as also in electrical engineering paper. So the question is stated as follows. In the circuit shown below, D1 and D2 are silicon diodes with cut-in voltage of 0.7 volt. Vin and Vout are input and output voltages in volts. The transfer characteristic is, this is the corresponding circuit and there are four options given here. So with a transfer characteristic curve, note that this is a curve between the input voltage and the output voltage. This is different from what we normally learn in analog electronics, where you have a plot of input voltage with respect to time, and then you plot another one where the output voltage is shown with respect to time. But this is a single curve which provides the characteristic between the input as well as the output. So the takeaway points from all these four options are that the transition points, these are called as transition points. Transition points mean that the points where the slope of the curve changes. So for option A, this is 0.3 volt and 1.7 volt. For option B, it is negative 0.7 volt and positive 0.7 volt. For option C, this is negative 1.7 volt and positive 1.7 volt. And for option D, this is 0.3 volt and 1.7 volt. And if we, let's say we look at one particular curve, what is the interpretation of this curve? It implies that the input versus output relationship has a slope of 1. It has a slope of 1 up until the input voltage reaches 0.3 volt. So this is the point. And the output voltage then becomes 1 volt. From 0.3 volt to 1.7 volt, the output voltage remains fixed. So the slope is 0 and the output voltage is at 1 volt. And then finally, beyond 1.7 volt, you have again a slope of 1. So the output and the input are related by a slope of 1. So likewise, you can interpret the other three options. Now observe this configuration for the diodes, and from our understanding of diodes, we know that this diode D1 should conduct current from left to right, provided we apply some voltage Vin, which can overcome the voltage at the cathode end. So the voltage driving into the anode should be able to overcome the voltage that is opposing. And then with this diode D2, it should be able to conduct current from right to left, provided the voltage at this anode side is greater than the voltage at the cathode side. So let's see how we can solve these sort of questions. So the first thing to do is we have to identify the states of the diode. That means when does the diode D1 turn on, when does diode D2 turn on, and when does they turn off. So let's proceed with when the diode D1 can turn on. So diode D1 can turn on if and only if the voltage at the anode side can exceed, number one, this 1 volt, and number two, the voltage drop that this diode will incur when it is in forward bias condition. So it is mentioned in the question that this drop will be 0.7 volt. And so it is easy to understand that if we apply a Vin which is more than 0.7 volt plus 1 volt, that means if Vin is greater than 1.7 volt, then this diode should turn on. And so if it turns on, you can replace this diode with its equivalent model. So this is the battery model that is used. And so the anode to cathode side, there will be a drop of 0.7 volt. And under this condition that Vin is greater than 1.7 volt, the output voltage, we can look at the left hand side of the circuit and we can formulate that V out is equal to negative of 0.7 volt plus V in. So V out becomes equal to V in minus of 0.7. Now under this condition that we have applied a V in which is greater than 1.7 volt and the V out turns out to be V in negative 0.7, note that the slope is 1. So you have a slope of the form y is equal to mx plus c. So what I am saying is that this value of m is 1 and then this is the intercept value. So if this is your V in, which is, let's say it's a sinusoidal signal like so, and maybe you have an amplitude of 2 volts or 3 volts, whatever it is, this diode D1 will start to conduct if and only if you are applying a voltage which is greater than 1.7 volt. So if this is the shape of the input waveform, the diode D1 will conduct only for this region of the input voltage. Now moving forward, we want to know what is the state for diode D2. When does it turn on? And so if we look at the position of the diode D2, this was the anode side and this was the cathode end. And therefore, if I have a 1 volt source on the right hand side, this is taking a drop of 0.7 volt, then the input voltage must go lower than 0.3 volt. So if this is 1 volt, this eats up 0.7 volt, I am left with 0.3 volt and I should only go down. If I go up, then this diode will be also off. But we are looking at the condition when this diode should turn on, and therefore the condition for D2 to turn on is that the input voltage should be lower than 0.3 volt. And then similar to the previous case, we can look at the output voltage and see that this V out is equal to plus 0.7 plus V in. So V out is equal to V in plus 0.7, where again, similar to the previous case, we have the slope equal to 1. Now also note that if I plug in the value of V in to be 0, so our input voltage has become 0 volts, then what should be the output voltage? And the output voltage is equal to 0.7 volt. So if I again plot for the input voltage versus time, and this is our sinusoidal signal, so the dashed portion is the one, this is the portion which is below 0.3 volt for the input, and this is the region for which the second diode, this diode, will conduct. By conduction I mean that it will incur a voltage drop of 0.7 volt, but it will allow current to pass through itself. Now we have seen when the first diode D1 can turn on, condition was V in should be greater than 1.7 volt. We have seen when D2 can be off and the condition is V in should be less than 0.3 volt. And so these are the two extremes. So whatever remains is in between condition. And for the in between condition, which means that V in should be exceeding 0.3 volt but less than or equal to 1.7 volt, under this condition both the diodes will be off. And so if both the diodes are off, so this is your D1, this is your D2, your input side is isolated from the output end because it's looking into open circuit for these two diodes. And therefore if I concentrate only on this part of the circuit, we find that there is a voltage source of 1 volt, there is a 1 kilo ohm resistance, but then if some current had to flow through this resistance, it would be looking into open circuits on either side. So the current I will be equal to 0, and therefore the output voltage is simply equal to this value, 1 volt. The drop across this resistance will be equal to 0 volt. From Ohm's law, we know that the voltage drop across a resistance is equal to current multiplied by the value of the resistance. So if the current is equal to 0, then this voltage drop will also be equal to 0. And so basically this 1 volt source is shorted to this point. So previous to whatever we saw, if this is your input voltage drawn with respect to time, and this is a sinusoidal voltage, so both D1 and D2 will be off within this region, which lies between 0.3 volt and 1.7 volt. So finally, we look at the transfer characteristic, which is what the question desired us to find out. And if we look at the various responses that we obtained, so the first one was if the input voltage was exceeding 1.7 volt, we found that the slope was equal to 1. In the second case, we found that if the input voltage was lesser than 0.3 volt, the slope was still equal to 1. And then if we had set the input voltage as 0 volt, the output voltage would be 0.7 volt. It came from the equation V0 is equal to V in plus 0.7 for this circuit. And then finally what we have here is this one, where the input voltage is greater than or equal to 0.3 volt, but it is less than or equal to 1.7 volt. And the output voltage was fixed at 1 volt. So this is a constant 1 volt output that we obtain whenever the voltage applied at the input lies between 0.3 volt and 1.7 volt. And therefore, because this is a constant value, so you have a slope of 0. So now if we go ahead and plot for the output voltage with respect to the input voltage, which is the transfer characteristic curve. So we know that the transition points are 0.3 volt and 1.7 volt. So these are the points where variation will take place. We also know that if the input voltage lies between 0.3 volt and 1.7 volt, the output voltage is fixed to 1 volt. So this is fixed to 1 volt. Now, if we look at the input voltage exceeding 1.7 volt, so this is the axis where the input voltage is exceeding 1.7 volt, the characteristic curve will have a slope of 1. So this has a slope of 1. And finally, if we look at the other condition, that is if the input voltage goes lesser than 0.3 volt, so we are looking at this part of the axis. This is the input voltage at 0.3 volt, and then we are going towards lesser values. The slope is still 1. So the slope is still 1, and then for the input voltage being equal to 0 volt, the cut point on this y-axis will be at 0.7 volt. So option A is the correct answer for this problem. This is a very nice problem. If our understanding of diodes, when does it open up, when does it short out, if these concepts are clear, then solving these sort of questions are not difficult at all.